Okay. We have this situation, net force is 20 newtons, acts 5 kilogram mass starting from rest for 10 seconds. Then I asked a couple of questions about stuff that's not familiar to you. Okay. So what are you going to do? You're going to puzzle over what this means, or you're going to take what I gave you and see what you can do with it. Okay. Well, that's the way you approach any problem. If you're not sure what in the world the ultimate goal is, do what you can with what you've got. And then all this might make sense. Okay, so what can you do with this information without looking at where you're headed? Okay, this is a big deal. Okay, this is what the next chapter is all about. Let's see how this works out. First of all, we take what we're given. What we're given is F net is 20 newtons. Mass equals 5 kilograms. So the acceleration was 4 meters per second squared. Okay. As soon as you see that you have a mass, a net force, and a mass, you automatically just use Newton's second law to calculate the acceleration. Okay, that connects the Newton's second law information to a uniform acceleration situation. Okay, so there we have it. We have this. V is 0, t equals 10 seconds. Okay. Now, intuitively, you can go to the equations and everything, but if you accelerate at 4 meters per second squared for 10 seconds, you get up to 40 meters per second, don't you? Okay. Equation of simple reasoning, just the definition of acceleration. We know that our change in velocity is going to be the acceleration times time. I'm going to use BF. BF equals 40 meters per second. You got to go to the equations, go to them, but if you understand what acceleration means, and especially since initial velocity is 0, but if you understand what acceleration means, again, you know that the change in velocity is 40 meters per second. Numbers are easy, do that in your head. Okay, V naught is 0. So the change in velocity is 40 meters per second. You start at 0, so the final velocity is going to be 40 meters per second. At this point, we can answer this question.
Question.
Okay, well, V squared is going to be 1600 meters squared per second squared. There's your change in 1/2 mv squared. Okay, well, now we want to calculate F delta x. Well, you have all the information you need to find delta x. The simplest reasoning is if you go from 0 to 40 meters per second squared, with the uniform acceleration, you average 20 meters per second squared. You do that for 10 seconds, you go 200 meters. Or 20 meters, I said 20 meters per second squared. You average 20 meters per second. Go from 0 to 40 meters per second. Uniform acceleration, you average 20. So we're all through this is working out. What did I do? Did something wrong. We go from 0 to 40. Average 20. 10 seconds, we go 200 meters. Somebody tell me what I did wrong. Delta X is 200 meters. I don't know why I was expecting to get 4,000 out of this, because you got to multiply that by the force. I was multiplying it by the mass, because again, what's I thinking? Okay, so and as I've told everyone else, we want to write F net X. That's what I want. Okay, net force times delta X equals $200 multiplied by your net force, which is 20 newtons. Which is 4,000 meters. A Newton is a kilogram meter per second squared. Why is that? Because force is mass times acceleration. So the units of force will be units of mass times units of acceleration. And you're going to get kilograms times meters per second squared. And you multiply that by meters and you end up with kilogram meters squared per second squared. Okay. Now you'll see. This matches this. Okay. So our lesson is in this case. You get this. Okay. Or F net delta X is a change in the quantity 1/2 mv squared. This is always true if you have a constant force, constant net force. If you don't have a constant net force, you replace these things with integrals. We'll see how that works, because that's what we're going to do. Now let me digress for a second, because that's what we're going to do. Like we've already done it in lab, sort of. So I'll make a connection here. Okay, this is a big deal. We can prove this, is always the case, just using the equation of motion. Okay. Instead of x minus x naught, we assume x naught is 0. We'll just say delta X, okay? That's like your expert can say tomorrow. Acceleration is F net over M, right? So what I would like you to do is plug F net over M in here where A is. And then rearrange it so you got F net delta X on one side. Everything else on the other side. Okay? So replace A with F net over M. And then isolate F net delta X on one side just to get standard algebra. Okay, this is a big deal, not that difficult. If we replace A with F net over M, get this. And we want to isolate F net over M. I'm F net delta X. Okay. We've got a 2, we've got an M here. Well, two ways we can do this. I'm going to just do this. I'm going to say, okay, 2. F net over M times delta X. Equals VF squared minus V naught squared. Subtracting V naught from both sides. And now, square it again. I put the delta X into the numerator here. Probably should have done it in this step, but otherwise, this is just what I wrote a minute ago. So I multiply both sides by M over 2, right? Yeah, just make sure. Have this, I multiply by M over 2. 2 is going to divide the 2, and the M is going to divide the M. I'm going to be left with just what we want, F net delta X. And then if I multiply this out, I'm going to get 1 now. So now, okay. Always so, we just proved it. If you accept Newton's second law and accept the development of the equations of motion, you have to accept this. Okay, now we've derived the equation of motion from calculus. Okay, so this has to be so if mathematics is consistent. Okay, and if you accept Newton's second law, when you combine these, you get this. And this is the basic conservation of energy. Because This is your change in 1/2 mv squared. And 1/2 mv squared is what we call the kinetic energy. Now, your book will probably abbreviate that delta K. It's okay, I like to use KE. Remind us from the very beginning what we're talking about. Okay, that's called the work energy thing. Because F net delta X is what we call work. It's the work by the net force. Okay. One more way of writing this thing. And we understand this is very simple. Just a little bit of algebra, and this comes out, at least for constant force and constant mass. And we'll address what happens for variable force, because you've already seen variable forces. When you put the cart on the incline with a magnet in the end of it, another magnet, brought it close to the magnet, there was a decreasing force that caused a change in kinetic energy. Okay. There were other forces involved too, so that's a little more complicated. But if you have that decreasing force, the F net delta X is replaced by the integral of that force with respect to X. And we'll address that. Right now, let's just stick with a really simple case so we get a conceptual view. And the calculus of it's very easy if you do the integral. And reason for the calculus, well, would be talking about that. Okay, so we have W net equals F net delta X. W net's the work done by the net force. Work done by the net force is always equal to the change in kinetic energy. And that cuts through a lot of stuff. We'll do some illustrations here in a minute. It cuts through having to use the equations of motion every time you want to analyze a situation where you've got a force acting on a mass. Okay. Cuts through a lot of conceptual stuff, and it cuts through a lot of mathematics. Okay. Not hard mathematics, could be done, but it kind of gets in the way of understanding what's really happening. So let's talk about a little bit about what might be happening here. If we have this, and we can take the original situation that I gave you, we have a 5 kilogram mass of 20 Newton force acting for 10 seconds, right? And instead of that, we could adapt it to a situation where let's say 20 Newton force acts with 5 kilogram mass through displacement of 10 meters. Okay. What can we conclude? Well, we can draw an immediate conclusion from this that we can't draw immediately from the equations of motion. What do we conclude if we know that the work by the net force equals a change in kinetic energy? Apply this principle and tell me what you can conclude from the information. Okay. Work by net force equals change in kinetic energy. Now, a lot of people are starting with the question of what happens to the velocities. You don't start with that question. You start with net force. Work by the net force equals change in kinetic energy. And actually, I think what I just said to you necessarily apply. Okay. So first of all, we can immediately do work by the net force. I gave you exactly what you need to find the work by the net force. You multiply the net force by the displacement. And I should have said net force. So don't be careless like I am. You want to always ask yourself, is this the net force or is there some other force acting? What is the sum of all the forces? That's what goes into this. Okay, well, that's just changing kinetic energy. And we can do this, right? And then we can multiply both sides by 2/m. Now we got a little confusion because m's mass and m is meters, but you just got to know the context. So VF squared minus V log squared is this. Okay. And this is 81. It better be 80 meters squared per second squared because these squared velocities are in meters squared per second squared, right? Like a note, Newton meter over kilogram. That's kilogram meters per second squared over kilogram. And we saw the kilogram meter per second squared a little earlier. So, you know, the units work out. Okay. Now, this is kind of confusing, symbolic with specific information. In other words, I've got my DS, that's where the V naught squares, but I got a real number over here. Would be to our advantage. Take a quick look. Symbolic expression. Okay, right there, we have everything, okay? So to answer this question by just writing the equations and then substituting the expressions at the end, you saw me get unbelievably confused when I put a bunch of units into an equation, simple equation, the up last, okay? And that should never happen. And really, I probably should have not done that. I was trying to make a point that probably did get back. Okay, anyhow, we got this. And what's this tell us about the velocities? What this tells us that by both sides by 2 over m, we're going to get a lot of good stuff here. Okay, so we get this. That's kind of a formula for the change in squared velocity. It's not a formula you want to memorize. It's something you can easily get from what we have here. So if I ask you a situation like that, can we draw a conclusion about the velocities? Well, all we do is we write out net force equals change in kinetic energy. So we've got F net delta X equals 1/2 mvf squared minus 1/2 mv naught squared. Simple multiplication tells us that the squared velocities change by this much. Now we could also write this. Look at this way, we're just using the concept of work. Now, if I tell you what the initial velocity is, so that you find the final velocity. So if we wanted to find Vf given V naught, two times net work over m plus V naught squared. Again, not a formula you want to remember, but something that easily derive. So I could easily have given you the question. Okay, it acts in displacement. It acts through displacement of 10 meters. If it starts at 20 meters per second, how fast is it going to be moving at the end? And here you have it. There's more we can say about that. We can say right now. I want to move on to another situation. Two masses suspended from pulling. Implicitly, a light frictionless pulling, let's say otherwise. And M1 descends through distance h. What's a change in v squared? What's the final velocity? V naught v. That's in terms v naught. Well, do this using this. Does the information I've given you allow you to calculate the work by the net force or the change in kinetic energy? Correct. Which would you rather try to calculate from the information? Well, you could do a change in kinetic energy. You get the net force divided by the total mass. You know, net force is going to be, if counterclockwise is positive, the net force is going to be m2g minus m1g, right? And total mass is m1 plus m2. So you can get this expression for the acceleration. Just divide the net force by the mass. And then you can calculate the final velocity, or at least symbolically calculate the final velocity. Okay. If you assume initial velocity to be naught. So that's what you used to do. Just the equation of motion and all that stuff. But it's way easier to calculate the net force, right? The work by the net force. So let's calculate that. What do you need to calculate the work by the net force? You need the net force and the displacement. So what's the net force? And, you know, when I say delta x, this isn't all moving along a straight line. At least two weights move in opposite directions. So we could use delta S instead of delta X, where delta X is the change in the position of the system. Okay. So talk about it for a second. Okay, so here's a little reasoning. If we assume counterclockwise to be the positive direction, then if M1 descends through distance h, that means M1 is going down, and this is going to rotate in the negative direction. So your del S is going to be negative H. Okay. What's the net force? Okay, so I'm asking what's the net force? We got to be careful about positive and negative directions. The answer I got was M1G minus M2G. Plausible explanation for that is kind of focusing on the motion of M1. So that's the first thing you think about. It's thinking of M1G minus M2G, which is going to lead you to contradict all of physics. Okay. So that's not going to work. You're going to find that, well, if M1 is bigger than M2, the system's going to slow down. Which is okay, so that's going to lead to contradictions. You want to be very careful. Your positive direction is counterclockwise. M2G, the gravitational force on mass M2, wants to accelerate the system in the positive direction. M1G wants to accelerate it in the negative direction. So F net, just the opposite of what we said. It wasn't a bad answer. Matter of fact, it was a great answer because it allows me to stress how important it is to do things carefully with getting all your directions right. So okay. You got to know your positive directions. So okay, so there you're at now. So W net is F net delta S, that's M2G. Minus M1G times negative H equals one half MPF squared minus one half MP naught squared. So that again, we can do a rearrangement. So I'm multiplying by negative H here. Well, first of all, we're going to get multiply both sides by 2 over M. Then we're going to get M1GH minus M2GH. And just be careful, this is mass total. M total equals this. Plus V naught squared. Okay. Now, what's the total mass? Total mass of this system has been accelerated by the net force. How much mass you got there? Okay, well, can't answer because I got the camera on. Okay. So I've changed what I wrote. I put the V naught squared back over here because the original question, what's a change in V squared? We want to answer that question. Okay. And I comment that M total is M1 plus M2 or M2 plus M1, whichever order you want to write them in. Yeah, that's going to go in the denominator. So you're going to have 2 times this all divided by M1 plus M2. That's not something you memorize. That's something you conclude by doing the analysis. And the analysis is really pretty simple. You're always going to have F net delta X on one side and 1/2 mv, 1/2, total mass, if you have to distinguish that, times v F squared minus 1/2 F total times v naught squared, okay? That's always going to be on the right side of the equation. What's on the left side depends on what information you're given. And the information we're given tells us very clearly, here's your net force, and here's your displacement. So it's a very simple scheme once you get used to working. You think in terms of energy, and you don't have to go through all the messy details you have if you try to work it out from mass, from acceleration and initial velocity, final velocity, all that stuff. Okay, not very messy at all, but messy, especially when I wrote it, but very straightforward. Okay. Okay, so let's take another situation. I got two of them. I'm trying to decide which one I want to do. Colors have time to do both. Okay, take the ball, full ball going up and down the incline. Okay. It's the only mass we're going to have, the mass of the pool ball. I need a symbol for the maximum distance. I don't like D because you sometimes use calculus. Call it S, not a 5 into that. Okay. Maximum distance is S. Not very with that side. Better to write it this way. Starts at X equals 0, turns around at X equals S. Okay. So find net force, F net delta X up, and F net delta X down. I'll just give you a mass of 0.4 kilograms. Okay, so I'm going to kind of work this through. Time here. You can easily calculate the acceleration up and the acceleration down. If you assume up is positive, going up, you lose 60 centimeters. Well, you're displacement is 60 centimeters. Your average velocity is then 15 centimeters per second squared. So your change in velocity, you're going from a greater velocity to a lesser. Your change in velocity would be negative 30 centimeters per second squared. Of course, you can always plug this into the equation of uniformly accelerated motion to do it. Okay. So this is going to be the result, and this is going to be the result going down. If you're careful about your signs, up is positive. It's clear that going up, you're slowing down, so your acceleration's in the opposite direction. Going down, your acceleration is in your direction, it's still negative. That of course is going to be your 0.4 kilograms times the acceleration. And that's going to be like 3 kilogram centimeters per second squared, which is going to be 0.003. And that down. 0.0024 minutes. So let's see. Work up is F net delta X equals what it equals, okay? And down.
Someone asking.
Equals what it equals. Your displacement is 60 centimeters. We're going to use J, stands for joules. And it's your unit of work, SI unit of work, it's kilogram meter squared per second squared, which I didn't have room to write out. And we want to quickly use that. Down here, it's going to be positive.
But the thing is, they are the evaluation.
0.00144. Okay. So
It's only silly and it makes it easier to think. That's how I want to.
your total, you add these up, it's negative. Point 0.00036. So what does this tell you about kinetic energy?
I don't have to think, got you there. So I don't have. Asking how YouTube works, you can illustrate and stuff. So many videos. Let's say you've got videos that don't even need that.
Second work was done, so kinetic energy decreased by 0.00036 joules, if I've got the numbers right. Now, the key is kinetic energy decreased from the time the thing started to came back. Now, why is it obvious that the kinetic energy decreased? Well, kinetic energy decreased. Okay, energy analysis, we should be totally familiar to. You can work through the numbers there and see if I did them right. The total work done
That's actually a pretty solid. That's.
It's not they don't. On the pool ball.
They don't.
negative to the pool ball. Lost kinetic energy. Kinetic energy decreased. How do we know kinetic energy decreased? Well, it's going slower coming down than it was going up because it took longer to get down through the same distance. So it was going faster when it started than when it stopped. And we can say that energy was lost in friction. And we could take total distance it moved and divide that into the energy lost to get the average frictional force. Okay, well, one example, it's something tangible that you've had your hands on. So